Hello, my name is Tankut Akgül. I'm an assistant professor at the Electronics and Communication Engineering Department of Istanbul Technical University. My co-authors in this work are Samet Özcan, who is the software development lead at Ednex MediaTek, as well as Alihan İplik, who is the director of product management at Ednex MediaTek. Today I'm going to present the Ednex cloud-based end-to-end server-side dynamic ad insertion, as well as the ad management platform for live content. So we felt the need for a completely scalable end-to-end solution for satisfying the broadcasters as well as the advertising agencies' needs at the same time. And this solution should not only provide a video streaming infrastructure, but also all the necessary tools for automated ad trading, ad management, and viewer analytics. For this reason, we developed the AdNext platform. Our solution is fully scalable, and it can easily scale to hundreds of thousands of concurrent viewers, which we have verified with various deployments in Turkey. And we chose to implement ad insertion at the server side because the client side ad insertion is more susceptible to ad blockers and may cause buffering issues on the client side. On the other hand, AdNext is a custom architecture, but when it comes to standards, we wanted to keep it conformant, especially to the IAB standards like VAST. And for the end-to-end architecture design goal, we have integrated a supply-side platform and a demand-side platform, SSP and DSP in short, with the video infrastructure. SSP is an ad management platform developed for the broadcasters for them to be able to manage their programs, schedules, internal ad placements for the live TV broadcasts. DSP, on the other hand, is an ad management platform developed mainly for the advertising agencies. And using DSP, the agencies may manage their clients' creatives, campaigns, and placements for the digital live TV ecosystem. So this whole system is currently deployed for the biggest for national TV broadcasters in Turkey. When we talk about ads, we are actually referring to two types of ads. One of these types is the targeted ads that we display during regular commercial break periods, defined by the broadcaster. The second type of ads is a single ad, and these ads are displayed outside the commercial break periods. We display a text overlay indicating that we will display a single ad only, and we also display a down counter on top of these PSS ads. One thing we noticed is that viewability with the PSS ads reaches up to 95% and completion rates even higher, up to 97%. In addition, as opposed to most mid-roll ads, these ads cannot be skipped at all. This picture shows the overall architecture of the AdNext platform. It also depicts the order of information flow between various elements in the system. So we basically have two subsystems. These are the video plane and the ad management plane. The video plane is mainly responsible for generating live video streams both in Dash and HLS format and stitching personalized ads into these live streams. On the other hand, the management plane is responsible for ad ingest, targeting, and analytics, campaign management. Video plane starts with the encoder cluster, and the incoming live stream, either from a satellite feed, for instance, or a multicast, is ADR encoded to produce fragments, Dash fragments, or HLS transport stream segments. And those segments or fragments are uploaded to a cloud storage server behind a CDN. When the user requests the stream as the first step, he or she makes a request to a component in the cloud, which we call the stitcher. And the stitcher is mainly responsible for generating an actual ADR manifest in either Dash or HLS format with personalized ads. The stitcher getting the request basically creates a session for every user and requests ads from the ad server. And receiving the manifest, the player starts pulling segments from the CDN and plays the content basically. When an ad is displayed, the player sends this tracking information that the stitcher adds into the manifest file to the ad server. And when the ad server is pinged, it gets the user information from the player and then stores that into an analytics database, which in turn is used to display all these metrics in the SSP and DSP platform. So let's have a closer look at the video plane. As mentioned before, one of the major components of the video plane is the encoder cluster. The encoder cluster runs in active passive mode and provides high availability. At any single point in time, only one of these encoders is actively encoding the incoming stream and providing those output segments along with the metadata that I'm going to show in the next slide. And the other encoders are in passive mode basically. And these encoders exchange heartbeat signals between each other using UDP unicast in a pub-sub architecture. When the available or active encoder becomes unavailable, one of the other passive encoders becomes the leader, an active encoder, through a leader election process. The encoder does not generate a dash or HLS manifest itself, as I mentioned before. As we will see, this is the stitcher's job. The encoder instead generates an intermediate file in JSON format that includes metadata for the stitcher. And this metadata contains track info, that is how many video tracks and audio tracks the stream has, bit rates and resolution, etc. For each track, there's a list of segments, including all the segment file names, their duration, segment types, whether the segments belong to a program content or an ad break or a program trailer, for instance, a scene with an embedded banner, etc. If there are any discontinuity in the stream due to this encoder switchover, this is also included in the metadata. In order to be able to replace ads during commercial break periods, we need to detect commercial breaks first. This ad detection is basically performed on the encoder. And the detection may be based on classical SC35 splice info sections in the transport streams. However, when we deployed this solution in Turkey, what we have seen that none of the Turkish broadcasters use SC35 at all. So we had to come up with an alternative solution to detect these commercial break beginning and ending times. And in Turkey, luckily, there's this Radio and Television Supreme Council. It's an organization regulating TV content, and they enforce visual markers for the ad start and end times during the commercial breaks. And here we see an example of these markers, and then a detection on the right-hand side in the blue rectangle. And we use two methods for this. One is the classical image processing method, which is basically searching for the template for this marker. And the second method uses the convolutional neural network, especially this mobile net V2 network, which we chose because of its lightweight implementation and sufficient performance for our purposes. And we use this second method in case the marker changes dynamically, its size or position changes dynamically. The other major component of the video plane is the stitcher. Stitcher maintains a separate session with every player, keeping track of ads that have been stitched, position in the stream, etc. for that particular viewer. For this reason, the stitcher is the main component in our architecture that needs to scale based on demand. The stitcher uses the intermediate manifest file posted by the encoder to determine the ad splicing points in the stream. And for the dash stream, each personalized ad is stitched as a new period in the dash manifest. So we use, as you can see here, a multi-period dash manifest. For the HLS stream, on the other hand, a discontinuity tag is inserted before and after every inserted ad. Naturally, this stitcher also talks to the ad server to request the personalized ads to be inserted in the stream for a particular viewer. The ad response contains ad tracking information, and Stitcher adds this information to the manifest file for the player to report that tracking information back to the ad management plane. We use custom attributes in the dash manifest file, as you can see here, to deliver extra information to the player. For instance, when a sequence of segments have an embedded banner ad in it, by embedded I mean a banner ad that exists in the original content inserted by the broadcaster, not by our system, the Stitcher can mark those segments using these attributes. Then the player may take extra action playing such segments, such as displaying a clickable link when those banner ads are displayed, or maybe preventing a banner ad that our system inserts from overlapping with an embedded banner ad, which will be an unpleasant situation for the advertiser. And for the HLS case, we use ID3 tags to insert this extra information for the player. One drawback of personalized live ad insertion is that you may introduce delays with respect to the original broadcast, and this is mainly because the total duration of the inserted ads may not necessarily match the total duration of the commercial break period. And what makes things worse is the PSS ads that we insert outside the commercial break periods, which increases drift even further. To solve this problem, we use the following approach, which I can explain referring to the picture here. So assume that there are two commercial break periods in the original content. one having a 30-minute duration and the other one having a 15-minute duration. And we want to insert two PSS ads, each having a 1-minute duration. So adding these PSS ads obviously introduces a 2-minute drift with respect to real time. And this drift is compensated in the first commercial break period. So we are reducing the 30-minute commercial break period to 28 minutes so that at the exit from this commercial break, we are perfectly synchronized with the live stream again. One thing to note here is that the targeted ads we add here during the commercial break period may not fill up this commercial break period completely, so we cannot completely fill up this 28 minutes. We can maybe introduce an overshoot here as well, but that's compensated using the same method in the following commercial break period by reducing its duration. Now let's have a look at the ad management plane. In order to provide an end-to-end service, we needed a user interface designed specifically for the live TV broadcasters as well as advertising agencies for them to be able to manage their inventories and campaigns. That's why we wanted to keep our interface as simple as possible, with everything contained in one place with adequate features. Behind the scenes, we have a highly scalable, lightweight ad server to provide ads to right targets, apply all the rules defined on offers, and collect view statistics. We designed our ad server with no single point of failure and no performance bottlenecks in the system. One of the main features differentiating our solution from the others is that the SSP is specifically designed for live TV. So that means we keep track of all the live TV schedule, which allows us to separate the programs, giving ability to publishers to configure their streams per program. That means they can insert ads on a program basis. For instance, publishers don't want live news to be interrupted by ads, so they can simply configure this using SSP interface to disallow PSS ads, for instance. Another feature is that advertisers can choose specific programs for their ads to be shown, which can be configured on the DSP side. This can be thought of as content-based targeting. On top of these, both publishers and advertisement agencies are able to get program-based campaign and performance stats, which help them plan their future campaigns. As part of our end-to-end service, we also designed our own player. This gave us the flexibility to design communication between our player and our ad server. We developed our player as VAST compliant with support for third-party tracking codes. With the collected data from our player, we present both viewer and ad statistics to our platform users. And our SSP and DSP provides detailed statistics near real time, differentiating us from most of the other measurement providers. To make our stream better and more stable, we collect detailed logs from each session separately as well. Our system also collects metrics from the players. We can collect real-time data from the players and log them at a centralized logging server based on ELK stack. We can view statistics about active users, playback stalls, total view time based on content, anonymous demographic and geographic distribution data, and so on. I'd like to show you a quick demo of our dynamic ad insertion technology. Here on the left-hand side, you can see our system with personalized ads, and on the right-hand side, the original live stream. And as I start playing them, you will see that the streams are currently synchronized. If I skip a little bit ahead to the first commercial break, you will see the markers that I mentioned before that shows up, and then we detect those markers and start stitching our personalized ads. On the left-hand side, you will see our personalized ads starts playing. On the right-hand side, the original ads from the broadcaster are playing. You will see we make these inserted ads clickable by displaying some overlays, and the user clicks the configured website for that ad opens up. And if I skip to the end, you'll see the exit from the commercial break period. On the right-hand side, the original stream returns back to the program. And since our inserted ads have a longer duration than the original ads, we return back to the program with a little bit delay. And as I mentioned before, this delay is compensated in the next commercial break. So due to time limitations, I cannot show you all the aspects of our system, but you can refer to these links that I included here to see more demos. In conclusion, our system is a fully scalable end-to-end video streaming, dynamic ad insertion, and ad management platform. We support both Dash and HLS streams. Our solution is compliant with the standards, which means ad metrics can be measured by third-party companies as well. Finally, our solution is already deployed and proven on the field. So this concludes my presentation, and I'd like to thank you for your attention.